Good morning, everybody. So this is the last lecture. So today I have three items in my agenda. So first of all, I would like to finish the description of dynamic discrete choice models and show you the application both in car ownership and in revenue management. Second, give you a brief introduction to the BIOGEME using slides prepared by my students for my class, and then try to have a look with you at BIOGEME and see how it works, what can be done, what cannot be done, and so on. Okay, so remember that I was Friday last week, I introduced dynamic discrete choice models. And remember that the main motivation for dynamic discrete choice model was to introduce a temporal variable into the choices, right? Because usually, actually we had the question yesterday, people asked, you know, people are making these choices, but do we know when these people are making that choices? And with static discrete choice modeling, you cannot do this. You need to introduce a temporal variable into your formulation. Remember that we defined a status variable, 0 if the consumer is in the market. For example, for car ownership problem, he is willing to buy a car, 0 if he is out of the market. We define two utilities. A terminal payoff, it means that it's the utility that you get when you buy a product. For example, when you buy the car. So you buy the car, you get your utility, and you get out of the system. Otherwise, you have another choice in this framework, which is wait, and still you obtain an utility that is called C, and wait and see if the market, if when you wait, it's kind of you have expectation of better quality product over the time. So this is, you see, this is the main difference, right? In discrete choice modeling, the static discrete choice modeling, the only thing we have, it's an utility that you get when you make a choice or when you buy a product. Here you have also this one period payoff, which is the kind of the utility that you have when you wait for something better in your life, right? So remember that we described both static and dynamic attributes. So these are the static attributes for the one period payoff. These are the static terminal payoff can contain both static, which are treated as usual, and dynamic, which are this YJT. The YJT, we said this follow a random walk. For now, I said we have a normal diffusion process with just one parameter. So that's what we do for now. And so this is kind of the new utility. It means that the problem is based on a kind of Bellman equation. Bellman equation is dynamic programming, in which you calculate the max between the utility of staying with your own product, which is the one period payoff plus the expectation of future utility, and the utility of buying. So this is your problem. So this is a kind of a Bellman equation in which you calculate the max between buying something, this is the terminal utility, or the one period payoff plus an utility that is coming from the expectation of future product quality in the future, right? So you have this expectation, and this depends on t minus 1. So you see that this is, so we have a temporal dimension here. So the D at t is function of the terminal utility at t, but is also function of the expectation of the utility in the future, right? So this is a standard optimal stopping problem. So it means that you stop when the utility of buying something exceeds the utility of waiting for another product. So this is some algebra. This is what we call reservation utility. Remember also that in the formulation we have dynamic attributes. And also said, with respect to the literature in economics, we don't solve this with the nested fixed point, but we solve this just with the maximum log likelihood estimation. So this is the way we do it. So once we calculate the probability of not buying, it means that the utility of buying is less than the reservation utility, and so you postpone. And at the end, given that you have this, you can calculate the probability of buying, and then you multiply the probability of buying by a logic in which you can choose which alternative you prefer, right? Which car. So this is, in the car ownership context, this is the probability of staying with your car, not buying a new car. This is the probability of buying a new car, and this is the probability of buying a new car multiplied with the probability of buying a certain type of car, right? Okay, so I'm going very fast here because we have already seen this. This is a kind of summary. All right, so we maximize this and we estimate the parameter. The problem is this expectation, right? The calculation of this expectation, because at time t, you need to calculate something that happens at time t plus 1. So in order to do that, given that we don't use this nested fixed point algorithm defined by John Rust, we have a kind of this algorithm in which we first calculate, so this is a kind of retrospective problem. So we start from the future and we arrive at the period in which we are analyzing. So this is a kind of stochastic scenario building in stochastic programming. You need to imagine that it's kind of in your mind. Suppose that you are in state T. So in your mind, you build a scenario tree. This is something that it's very popular now. If you attend conferences in stochastic programming, which I do sometimes, they are talking a lot about this scenario tree, because everything in stochastic programming is based on scenario, right? That gives the incertitude. So this is something similar, because suppose that you are now at time t, and suppose that you have a dynamic framework over time, right? So you want to analyze time t is plus 1, time t is plus 2, and 3. So you have a number of time periods. For example, in our car ownership, you had a scenario for each 6 months. Each 6 months, I was giving you new alternatives. So it means that you have a scenario every 6 months, and we had 6 years, so 12 scenarios. So this goes from t equal to 0 to t equal to 11. So at each time period, your choices are I buy, not buy, right? And if I buy, I also have choices between gasoline car, plug electric vehicle, and hybrid, right? Now, you can build these scenario trees in different ways. You can build this way. You can build this in this different way. For example, suppose that you buy, and then I can say, okay, when you buy, S is equal to 1. Your status variables is equal to 1. So you go out of the market. Because, well, for several reasons. Because I don't expect you to buy another car in the next few years that I'm analyzing, or because it's too difficult. In fact, it is difficult to solve this repeatedly over time, although we do it here, because here it's mainly trying the methodology instead of having a realistic problem solved. We wanted to see if we were able to estimate this by combining this kind of ideas. And then, but if you stop here you don't stop, because again, you have a choice of not buy and buy. And here you have again gasoline, PEV, electric, and hybrid, right? And you go ahead. So your tree is growing that direction. But in some cases, for example, not durable consumer goods, you can buy, for example, a computer. You can buy a computer every 2 years, right? So in that case, you will have this growing both sides. So this is the way we see the problem. So we introduce this scenario tree building, which is taken from stochastic programming. So I'm doing this also because I have a colleague, my colleague in mathematics, who does stochastic programming. So we joined. So I had the problem. I said, look, what can we do with that? And he said, well, why don't we use stochastic programming? And he was right, because I'm seeing now many people presenting problems that are not in this context, but solved this way. Okay, now remember that every time you decide, for example, here, you have this one period payoff plus E of some utility at t plus 1, right? So it means that when I decide here, I have to have this value here. And what we are doing is retrospective, in the sense that we start to calculate this E. So we started to calculate this E, and for now, what we do, we say people have expectation over a limited time period. For example, two periods. I know that this is a strong assumption, but as I said, this was a trial. Given that there is nothing in transportation like that, we say, and given that my student, she was very worried, she wanted to graduate, because she was given this problem, and she said, oh my God. We assume that E at time 3 is equal to 0. So you have expectation just over 2 time period. So when you calculate at 2, you know that E3 is equal to 0, and so on. And so you bring up this expectation of this utility, and of course this is a stochastic, so you need to make simulation of the different alternatives available at that time. And that's what we do. We calculate expectation, we calculate the reservation utility, then we calculate the utility of not buying, and then the utility of buying, right? So can you see this bringing a retrospective way of building the problem? So this is the scenario tree. You see what we are solving here, right? So for now, that's what we have, and we consider the entire tree. So our tree for the car ownership is growing both directions. You will see also an application in which it's growing just one direction. And if you see here, you have that the expectation of time period 3 is equal to 0. Then you can calculate ED2, ED1, and then you put ED1 here in ED0, in time period 0. All right, so this is what we do. There is a lot of simulation embedded here, because all these expectations are calculated are simulated, and there is a double simulation, double simulation, because this is stochastic, and what it is also stochastic, remember, is y, the dynamic attribute. So we have we draw twice from this expectation and from the y, the dynamic of the evolution of the industry over the time. So there is a double simulation going on here. This was our dynamic discrete choice framework, and let's see what we have done with that. So I have two applications. This is the application on car ownership. I'm very careful with this number because I have very few respondents. You see that here I have 50 respondents. So it's not for the numbers. This is to see if we were able to calibrate that model and if the model made sense. So the second application is better on this respect. So as my reviewer is saying, I have this under review, but it's almost accepted. He says, oh, this specification is odd. Yes, I know. With 50 respondents, there is very little you can do, and also the problem was very complicated. Getting this data was a nightmare, so I said, well, he said the mathematics is good, so he's going to accept this. Okay, so this is less or minus what we have in that model. So this is the dynamic discrete choice model calibrated out of the stated preferences that you have seen many times in these 8 days. So we have, this is my students that she doesn't have, so this is the alternative specific constant of hybrid, this is the alternative specific constant of electric, and this is the alternative specific constant of the current car. So gasoline is kind of the base of the model. We have an MPG when you know the MPG of your own car. This is the MPG when you don't know the MPG of your own car. Vehicle age, price, static, price dynamic, and range. Well, actually, it's not that odd. There are all the variables you want. Let's see. So here, although I have very few respondents, less or minus, these coefficients are significant. This is because before we did a lot of cleaning. But look at this. So the multinomial logic cannot estimate the alternative specific constant of the electric car. And this is causing, you will see later on, a lot of problem in the application of that model. The rest is fine because this is positive, and this is much bigger than this. So it means that if you know your MPG, you are much more sensible to the MPG of the new car. Vehicle age is negative, meaning that, and this in the utility of staying with your own car. So it means that the older your car, the more you are willing to buy a new car. So it makes perfect sense. So we said price static, which is the price of the car for both gasoline and hybrid. Of course, we don't have a price on the current car because you already bought it. And we say price dynamic here. So the Y, remember the YT, the industry evolution, this is the price of electric car. Also makes sense because you expect that if technology is mature enough, the price of the electric car is going down in the future. So we were able to estimate this. This is the range for the electric car. Actually, it's not, there are no social demographic, for example, because there is not much heterogeneity in this population. So it's true, can be better, the specification, but these are all the variables we wanted. And the dynamic one, you see that E is able to estimate the alternative specific constant of the electric car. So it means that it's giving better result. The rho squared is much better than before. And in application, this is the way we regress. Remember the y, t+1 function of the yt? This is the price of the electric car. Now, this is derived from our own data, from our own stated preference data. It's not really a random walk because you see that this value is very low. So it means that the price of the electric car at time t+1 does not depend much on the price of the electric car at times t. So it means that it's not really a random walk the way we wanted, but because of the way we collected the data, because stated preference, they are quite independent. Stated preference, the attributes are quite independent from a scenario to another. This is actually another thing that we needed to solve, how to make this scenario dependent. And some people, they say you don't want this scenario dependent. So the way to collect the data is also going to change. But anyway, if you see, I don't have here, but if you see, we have done this also for the price of the fuel over time. So we had 30 years of fuel price in the United States, and we estimated a random walk on that. And you see that this coefficient is 0.9. So it means that there is a lot of correlation between price at different years over time. So again, ideally, you should have both, and you should have a lot of data to calibrate this kind of stuff, but this was just a kind of trial. In the application, this is kind of out-of-sample, no, this is not out-of-sample validation, but we are applying the model at different time periods. You see, we have 10 time periods, and this is the error that we make with the multinomial logic, and this is the error that we make with the dynamic. Well, they are close, but this is doing okay. what I get from this, these are the forecasting. You see that the difference between a static discrete choice model and dynamic discrete choice model. When you have a static discrete choice model, you have just projection, but you never have time, right? Here we have a projection over 10 time periods. So what happens here is that, as I told you, the multinomial logic is very wrong with the electric car. And this comes from the fact that it was not able to recognize, it was not able to estimate the alternative specific cost of the electric car. So this is one point. The other thing is that overall, and if you have been calibrating multinomial logic like me all your life, you know that multinomial logic is very good in averaging things. It averages everything out. And you see what's happening. You see, this is the static model, the multinomial logic. So it's kind of averaging a behavior. So it cannot capture this stuff. You see that the dynamic model, although it's wrong sometimes, but it can mimic the curve of the real data. That's, I think, the main thing we can, well, this is not very accurate, again, because you have 50 respondents. So if you start to have 500 respondents, I expect this to be much better. But I was kind of very nicely surprised about, you see, this kind of being able to recognize that there are peaks in demand and so on. These are all the people involved in this. So Renting Shu was my student. She graduated 1.5 years ago. Michael is still working, and Fabian is my colleague at University of Montreal, who does all this mathematics stuff. We have a nice application with a lot more data in revenue management, and I understand that here there is also some management involved in this program. So maybe you will be interested in this. So what's the story behind this? If you look at the literature in revenue management in the last 10 years, you will realize that these people have discovered discrete choice modeling. And because they are confronted to the different choices, for example, in many cases is ticket purchasing. It's buying ticket for flight, or buy ticket for, or buying a stay in an hotel. So they do mainly airline revenue management, or they do hotel revenue management. There is something in railway revenue management, especially in Europe, because they have the high-speed rail service, which is kind of an airline service. So these people are not in transportation. These people are OR people. These are people in operation research. One of the most famous papers in revenue management that implements discrete choice modeling is a paper from Tallur and Van Ryzen, in which they say that demand should be modeled with the discrete choice models because it gives a realistic framework to model choices, and it gives behavioral insight that they could not achieve with just aggregate demand modeling. Now, the other thing that you should know, and it's not here, it's that this discrete choice model are embedded in an optimization framework. So they see the dynamic the discrete choice model as a component of an optimization framework. So they are very good. So if you see their presentation, they are mathematically very, they are heavily mathematical presentation, so they do mainly optimization with a component of discrete choice model. Now, if you also see their presentation, there is a lot of confusion about what a discrete choice model is. For example, a mistake that I've seen many times, they call latent classes a mixture of models. So they confound the latent classes with mixed logic, which is very, very different. So every time they present a mixed logic, and then they have a mixture over two classes. Also, for example, I've seen a presentation just before coming here in Rome at the beginning of July, in which a very famous guy was just presenting nested logic without results, just the theoretical framework. I said, well, nested logic we calibrated 20 years ago. And the other thing is that what you see, what they have is very theoretical, in the sense that They have a very nice framework, but they are very difficult to estimate in reality. So it's interesting to see that they are doing this and also the new approach. So for new PhD dissertation, maybe this can be a topic. So that's what we did 4 or 5 years ago with a student of mine. I had a very good student from Thailand, fantastic student. So I decided to explore a little bit this revenue management topic from my point of view, from the discrete choice analysis point of view. So I have several applications that I've done with Pratt, several applications. So we have a number of papers with Pratt. And also Pratt has got a job in this area. So he has been hired by a company in the United States who wanted to do this kind of revenue management. So there is market outside. So we have a number of applications. We were lucky enough, we have real data, and this real data is from railway. So this is revenue management for railway and for kind of high-speed services. So it can have application here, it can have application in Europe. I'm hoping to be able to present this at the Dutch National Railways because they are just introducing high-speed rail there. They have a problem with the trains. The trains, they don't work. The trains are Italian. It's a big shame for me, but the train have a problem. So it seems that the mechanic of this train is something is wrong. Anyway, we have a number of papers, but what I'm presenting here, which is the dynamic discrete choice model applied to revenue management, is for a particular problem in revenue management, which is ticket cancellation and exchange. So this is very important also for airline. When you cancel, they say that it's about, for them, a 10% of the market. So it's very important for overbooking and so for them it's very important problem. Here is also important because the policy of this operator is kind of very flexible. What you can do, you can buy a ticket and then give back the ticket without paying any penalty. And you can change everything. You can if another ticket is available, you can change origin, you can change destination, you can change departure time, you can change day of the week, you can do everything without paying really a penalty. You just pay the difference between the price of the new ticket and the price that you paid, which I think is very inefficient, but that's the way it is. We have also another difference with the problem in transportation is that you have an unbelievable amount of observation because this is just internet ticket sales. And you see that you start to have in the order of 100,000. So we have 155,000 reservation record. But the problem is that you don't have any social demographic attached to this. So if you want to do pricing, you need to know the characteristic of the people, and you have nothing about this. So there are different problems. The techniques can be the same, but the problems are different. So you see that the exchange cancellation is significant in the sense that we have 18% of the people who exchanged or canceled somehow this ticket. So there are 20% of these people that did something with their ticket. Now, we also simplify the problem again because we want to apply this dynamic discrete choice modeling, so we wanted to stay in a reasonable framework. So what we do is, I don't have this. So what we do, we say we consider those who exchanged one time. So we say that if they exchange one time, they are out of the market. We don't allow them to exchange multiple times. And we also said that we consider just those who reschedule the departure time. So we do not consider those, for example, who are exchanging OD, and so on. That's what we do in reality, right? So we model these people and these people. So no reschedule or OD change and reschedule of departure time. Well, this is our assumption, but for now it's good enough. The other problem that we face here, and so for now we also consider just people. This can be extended easily, but just to have a nice framework, we say that we consider people who bought the ticket 50 days before departure. We are under this assumption. Let's see what happens. So at the end, I don't have many individuals, but anyway, I have almost 700 individuals, which is much better than my 50 individuals before. So this is what happens, right? So I start here. So this is my temporal horizon. So I start here, which is day 16, which is 15 days before departure. Another way that, another assumption that we make, but this is also what the operator make, in the sense that they told us this. They say that, you know, all this buying, exchanging, and canceling happens within 1 month. So there are not many reservations that happens earlier than 1 month. So our temporal horizon total is 31 days. And so here we start at day 16, and we start, so for example, so these are the trains that are available, right? So this is the kind of train that you can buy. So there is one at 5 a.m., one at 6 a.m., one at 7 a.m., 8 a.m., 9 a.m., and so on, right? So there are these trains available. So we consider also departure time. So suppose that I buy a ticket for a departure from my origin and destination, given that this doesn't change, for 9 a.m., right? So then I buy. Then every day I have the option: I keep the ticket, or exchange the ticket, or I cancel the ticket. And for example, I decide that at day 6, what I do is that I exchange my ticket, and then I depart on the day 16. The scenario 3 is this way, right? So at each time period, let's see, I buy the ticket. At each time period, what I can do is keep the ticket or exchange the ticket and change for another departure time, or I can cancel, right? So if I do that, I'm out. I'm not anymore in that system, because my assumption was that I can exchange or cancel just once. Or otherwise, if I keep the ticket, my tree is growing that way. We have a comparison between multinomial logic and dynamic. This is the simulation. So this is kind of simulated data, in the sense that we used kind of the real data, but we suppose that the coefficient assumed some value. We calculated the choice, and we estimated this with both multinomial logic and dynamic discrete choice model. So you see that here, these are the true value. These are the value obtained with the multinomial logic, and these are the value obtained with the dynamic. And you see that there is a lot of bias with the multinomial logic. So the dynamic discrete choice model does much better in recovering the true parameters. Although this is not a fair comparison, because we needed to do this, to redo this, but we assume that the process is dynamic. So we say, what do we lose when the process is dynamic and we estimate it as a static? This is also reflected, of course, in the prediction, because you see the bias here and the bias with the multinomial logic. So the dynamic discrete choice model does much better than the multinomial logic. Although I agree that it's not a fair comparison. You should see this as what we are losing when, instead of having, for a dynamic process, when we apply a static model. These are, again, the application. And what is the problem here is that the multinomial logic is very wrong in calculating the exchange behavior. So multinomial logic overpredict the exchange behavior, while the dynamic model, it does quite well in reproducing this exchange behavior. So this is exchange, this is cancel. Both dynamic and multinomial logic, they do almost the same. And this is keep, in which, again, the multinomial logic doesn't do very well, because underpredict the keep alternatives. So this is about exchanging. You see that you can also apply this to the different departure time. So you have cancel, and you have exchange for the different departure time. This is real data. So, so what you have seen before was simulated data. This is the real data for which, of course, we don't have the true value, right? Let's also see what kind of variables we have here. We said that we don't have any social demographic characteristics, so don't expect to find income or gender, or so it's not possible. So we need to kind of find proxy for this variable. So what we have is that, for example, we have one party size, more than one passenger. So it means that it's very likely that if you are with more than one passenger, it's not a business trip, but it's more a leisure trip. Then you have departure time, which is in the morning or in the afternoon. Again, it can be a proxy of purpose. And if you depart on Monday, on Friday, some variable specific of the destination, these are important stations. I cannot reveal you which station are these, because otherwise the operator will be very mad. But these are kind of important stations that we found that there is a particular attraction of that station for that day, for that time. This is the exchange cost, the refund. Again, this is something that affects the utility of keeping the ticket. Day from here, so how much in advance you buy the ticket. If you cancel on day 1, if you exchange on day 16, and an early exchange. So you see that there is nothing about social demographic. That's a proxy of kind of the social demographic. So what we have here? So we have that departing between 5 and 9 is positive, this is negative, and so on. So we have all kinds of. So the good news is also, so one of the main, we were really worried about being able to estimate this. These are quite difficult, all this expectation, double simulation, calculating the log likelihood, maximizing this. So our objective was really get this estimated and see how they do. Also, you see that for the validation, also for this is kind of fair in the sense that this is real data. You see that the bias in prediction of the multinomial logic is much higher than the bias of the dynamic discrete choice model. So we get good results on that respect. Again, the multinomial logic somehow is wrong in predicting this exchange and in predicting this skip behavior. Although now this is kind of less, it's not like before. Before there was a huge gap. Here there is less gap. This was to say that these are all the new area of research that we are exploring. Revenue management and application of discrete choice modeling in revenue management is something that can be done, and I would like to see more of our community working on this, because also there will be more exchange with these people in OR. We have to learn from them about all the nice optimization framework that they use. And also they can learn from us, because I think we have more experience in calibrating these discrete choice models with real data. And also you have seen 2 applications of these dynamic discrete choice models. There might be more. For example, we are exploring now with a student of mine about behavior during evacuation. Because predicting the time when people start to evacuate, when they listen to the message and they start to evacuate, is very important. So the dynamic in this problem is so just on the network side, never on the behavioral side. So we are exploring this. We have also data surprisingly collected by another university, and they gave us the data because it was federal money. So we have dynamic behavioral data collected for free. So we hope to be able to apply this. I also wanted to say another thing about this. So here you don't see any optimization framework with the dynamic discrete choice model. But usually what you do is, I don't know if I can formulate this, but what all these people in revenue management are doing is, once you have the dynamic discrete choice the discrete choice model estimated, they don't do dynamic. So once you have the discrete choice model estimated, you can calculate the probability of buying at certain period of time, and you have also the sensibility to price. So you have a coefficient for price estimated. you put that into an optimization problem in which you maximize revenues, given that you have the sensitivity to price, and then you can calculate the price of this ticket, optimally calculate the price of this ticket. And the other thing is that if you also know the characteristic of the individuals, you can adapt the price to this characteristic of the individuals. You can adapt the price over a certain temporal horizon. For example, you can decide to give ticket cheaper in the beginning and then increase the price at the very last minutes, where people, they don't care about price because they are traveling for business, they are reimbursed. Or if you have too many seats available at the end, you can decide to lower the price and give these seats away in order to fill the train. Okay, so that's, I have more of this. It's not just organized, but if you want, I can send you the thesis from my student Pratt that was quite well written. It was very good.
The first step to develop the dynamic choice model, you need to segment, divided the study horizon into steps. How to decide to?
It depends on the problem, because for ticket cancellation and exchange, this is easy. It's every day. For car ownership, we say every 6 months, but in my opinion, you can do every year. Every year you can. For this evacuation problem, I don't know what we have, but we have kind of 3 stages. They call people who evacuate early, people who evacuate in the middle, and people who evacuate at the very end. Now, what they mean for that, I don't know, because I haven't seen the data. So it's problem dependent. However, this is not the main problem. The main problem is having the data. And the models are difficult to estimate. The guy, so John Rust, as I said, I organized the workshop at University of Maryland. So the big boss in dynamic discrete choice model, he agreed to give a presentation. And what he presented was a very nice application on the optimal time for a rental car company to exchange their car, to get rid of their car. And so it showed clearly that these companies, they were giving up the car too early. And by keeping them for another year, they were making a lot more money. And actually, he was working with a company from Asia. I don't remember exactly the country, but the company was from Asia, because in the US, they refused to give him data. So he from Korea maybe, he got data from Korea, and he was showing this. Actually, they implemented with the company the policy. So there was so it was just not a study. He had the real results. So he was able to show us the results before the policy implemented and after the policy implementation. So he had a real world application. So if this is another thing that we need to improve, work with the companies. When I presented this to the train operator, they were really worried, because they said, oh, you are working against us because we receive funding from the government. And if you show these results, you show that we are inefficient. And so they will give us less money. So in fact, now I never say which is the operator. So this is also something that I found it difficult to communicate this kind of results in a positive way.
Is it possible for this kind of a model to investigate the effect of habitual?
The effect of?
Yeah, habitual. Because we make some decisions not necessary to maximize our utilities. It's just because I do that yesterday.
Yeah.
And I'm habitual to do so again.
Well, this is there are two problems I see there. One is this kind of study on inertia. The fact that I've done a choice yesterday will make me doing the choice again. So, and the other is, I don't know, this framework in which you don't necessarily maximize your utility, but I'm not very familiar with that. So what they do when you violate the hypothesis of utility maximization. No, I've never really looked into this, so I don't know. But there are studies about this inertia, trying to separate the effect of inertia. But I don't know how advanced they are in this. So do you have any, so here is management, do you have any faculty or students working on this kind of problem, working for?
Dynamic?
No, revenue management.
Yeah, sure. For airlines.
For airlines.
For airlines.
For airlines. Okay.
Most of the model is from OR.
Yes.
Not from logic model.
Yes. Yeah.
I can see why they do that, because if we use the logic model, we only know the choices. We don't know how many passengers do so.
Yeah,
we
this.
need to know how many passengers.
Yeah, this is well. This is actually the paper from Talluri and Varisen. Do you know the paper? No, but it's exactly what you are saying, because they work. The main difference. So today is the last day, so we can have more exchange. So the main problem they face in revenue management is that they don't observe all the choices, because if you are an airline operator, suppose that you are United, you observe your own passengers, right? You don't see the other ticket. You don't see the sale of the concurrent the other operator. So if I'm United, I don't see what American is selling. I know less or minus that there is a market there, but I don't know when these people bought the ticket, at which price, and who these people are. So this is called censored data. So it's kind of censored. You just observe one part, your own part. You don't observe the rest. So the paper of Talluri and Varisen is exactly about this. They have a model based on expected maximization, in which they can recover the parameters even if you don't observe this part of the market. It's low, but at the end they have results. Although they have results on simulated data. In this discipline, you never see real data. But anyway, they have results, and this paper is kind of the masterpiece of revenue management with this choice model. Now, so this was a paper in 2004. Now, just to show the interest of, so I've just reviewed the paper for Transportation Research Part B, in which people from transportation suggest other way to estimate that. And actually, I think the paper is going to be accepted, so you will see the paper. You know the people. And they suggest other methods that are closer to what we do, and they have good results, and are the estimation method, it's easier, and it takes less time than these people in revenue management in OR are doing. So I expect more people to work on this in transportation. We have something to say, that's my point. Yeah, but this, what you are saying is exactly the problem they face. So I'm going to subject number 2, and I'm perfectly in time because it's 11. All right, so this was prepared by another good student of mine who is still with me, but not for long. She's going to graduate in October. So she prepared the tutorial for BIOGEME. So I want to let you know that I don't really know BIOGEME. So in the sense that I've never really used BIOGEME for my research. When I was young, I was using Elogit because I was working with the guy who wrote the software, who is Andrew Daly. So the story is this. I don't know how many. I want to tell you something about the software, what it's out there. Okay, so you know Nlogit. This is wrote by William Greene with the help of David Ensher. So the brain, it's also David Ensher there. So he's suggesting what to implement at what time. Well, NLogit, I don't know what he does, but I think he does logit, nested logit, probit, and mixed logit. I don't know if it does GV. I don't know. But this is, you need to pay for NLogit. It's not that expensive, right? Or it's not that expensive. You can. Sometimes I don't really trust the optimization routine that they have there, because we have tried several times to estimate some models but never succeeded. Then I worked with Logit, which was developed by Andrew Daly. This is also for, you need to pay in order to use that software. So this software doesn't do much. It does logit, nested logit, and mixed logit, but not much of a mixed logit. It does just mixed logit with normal random variables and error component. But logit is very good for those who are working in consultancy, because it's all you need in consultancy, right? You need to calibrate logit, nested logit, and you work with multiple data sets. And this is very good in joining model data set together, in joining model together, and it's very good in estimating joint RP and SP model. So if you are in a consultancy, actually my students, they always start from Logit. They clean the data in Logit because the interface is very nice. You can work with multiple data sets, and my students, every time they try one of these fantastic advanced discrete choice model, they need to have a Logit model that works. So you need to spend some time on the Logit model, and working with the Logit makes your life much easier. So that's what also Alice is doing all the time. She has a model calibrated in a Logit. Once she's happy, then she transfers this model into an advanced discrete choice model using our own software. Well, this is what I'm showing you. This is BIOGEME. BIOGEME is for free, and it's. I'll show you how to download BIOGEME. And it does many things. It does, I will show you what it does, but it does logit, nested logit, all kinds of mixed logit with all kinds of parametric and non-parametric random coefficient. It does GV, it does latent variable, it does latent classes, and also what he has now a module in Python. You can program your own model and give him to optimize. So for example, my students, Michael, he was trying to have the dynamic discrete choice model estimated in BIOGEME. He never succeeded, but in principle, if he spends more time, it's possible. The problem is that he solves this with finite differences, the optimization, and so this, it's true that it's very general, but it's also very slow. So, you know, there is a trade-off. When we implement software in my group, we have always this trade-off between writing a software that is adapted for that problem or writing a software that is general. I don't know why we are always writing something that is specific for our problem. At the end of the day, that's what has happened in my group. So this is BIOGEME. Many people working in transportation are using BIOGEME. I would say 80% of the people are using BIOGEME. It's because it's also for free for the students. You know, it's very convenient. A first approach with discrete choice models, you download BIOGEME, and then you can have many things done. Other software that are out there. So CanTrain, he has a software. It doesn't have any name. So CanTrain web page. You know, CanTrain is the father of mixed logit. He's very well known. He has a number of resources in his website. He even has lectures, videotaped like this. And he's very clear. He always wins. The prize for best teacher of the year. So if you go there, there are papers, lectures, and there is software. Now. This software, again, you can just do, if I'm not wrong, probit and mixed logit. Well, you can also do logit. But mainly, there is code for mixed logit. So we have all learned the mixed logic from his code. It's before it was in Gauss, so he has two versions. One is in Gauss and another one is in MATLAB. It's open source, you can open it and do whatever you want. It's also for free, everything is for free there, even his book. Many of my tutorials here were based on his book, and the book is for free. You can download chapter by chapter the book, so everything is there. My students, I work with the mathematicians, so my students, when they see his code, they don't like it, in the sense that they say it's very inefficient, it's very difficult to understand what's going on because there is no structure. It's just 5,000 lines of code, and you are easily lost in the optimization routine, in the atom rows, and so on. So it's in order to modify it, and in fact, I have not seen many people modifying that code. But anyway, and it's also slow because it runs in MATLAB or Gauss. So if you have a very complicated problem, it takes days to estimate. What else? We have a software, but it does just mixed logic. And again, the way we are working, I don't know why, but we have Hamlet is also for free, does mixed logic, and does mixed logic with the random coefficient, error component, panel data. It does parametric and non-parametric, so you can do normal, log normal, triangular. It does all this distribution. So mainly with our software, you can do mixed logic. And I think that's mainly it. My students, I don't know if you already, I think in his website, but I don't even know which is the name of this website, but his name is Jean-Michel Tremblay. I think he has made available the software for the discrete continuous that we have. And I think he has also something on ordered logic, ordered probit, ordered logic, and ordered probit with related classes. Or if you cannot find it, write me an email and I will arrange for you the software. Our next step is to have available this dynamic discrete choice model software, but this I think will take a year because we have something that is running but is very badly written. So we want to go, I have a project for that, I just got money for this. So if my Canadian student is in a good mood, he's a mathematician, so see, if he's in a good mood, within a year, we can deliver that software. Let's see if I can do this. Huh? Yes, all we do is for free. All we do is for free. All right. Okay, so this is the overview of the software that exists. Almost all the software, they work this way. So you need to define some. Who has seen BIOGEME before or NLogit? Who has been working with NLogit or BIOGEME? NLogit. For estimating what? Multinomial logic? Nested logic, okay. It works well?
Very good.
Huh?
It's a good software.
So it's able to estimate all the model that you have tried, all kind of nested structure?
Yes.
Okay, it never got stuck?
My model is not that complicated.
Ah, okay. All right, but anyway, it's good news. Well, it's many people, they use NLogit, so it's a good software. Okay, so in all the models that you estimate, you need to, so this is a kind of brief tutorial. And again, I don't know BIOGEME well because I've never really used it. Now I'm not running the model anymore because my students are running the model for me, so I've kind of lost the practicality of doing this. So all I do now, I give idea, they do the work, and then I write the paper. So the job change over time. So you need to specify the dependent variable, so the utility, right? The utility, let's say this is the utility. Then you have to specify the alternatives, the attributes in each utility, and then the model form. Oh no, she says the dependent variables, I think this is the choice. The alternative, so the choice. How many alternatives you have, the attributes, which means all the independent variables, which are the x. The model form that, for example, is multinomial logit, nested logit, I don't know what, binomial logit. This should be binomial logit. And then you need to specify the utility. So it doesn't matter which is the software that you use, you need to do this. This is what he does. He has an example. He has a data set, which is called the Swiss Metro. We will see that later with my computer. So he has a data set, and he applies all this model to the same data set. So you can see the evolution is very good for the educational point of view. You can see the evolution of the model from MNL to NL to mixed logit and so on. So he has a very simple model. But you see that he has three alternatives. The three alternatives are the train, the Swiss Metro, and the car. And he has travel time and travel cost. You see that he says travel time and travel cost is scaled. I think he divides this for 100 for computational issues. So the optimization is easier if he scales this variable. But you know that multiplying a variable by the same number in all the utility doesn't make any difference, right? Because adding or multiplying by the same quantity doesn't change your model. These are the x, right? Train time, train cost, Swiss Metro time, Swiss Metro cost, car time, and car cost. These are the variables to be estimated, together with the alternative specific constant. Now, there is something that I don't like in BIOGEME, is that he says, you know, there are three here, which is not feasible, but he wants you to fix one to 0. So you need to tell him which one to fix. I think this is very counterintuitive, because I expect, for example, this to not be there. This is a lot of confusion with my students. When I start calibrating model, it generates a lot of confusion. But anyway, this is the way he does, so let's do this way. You need to specify where is the data file, which needs to end with .dat or txt, and you need to give him a model specification file, which is .mode. Again, this is also another problem, because when you try to open this, Windows thinks that it's a movie. So it brings you to a movie opening stuff, and then it gives you the output file, which is HTML. This is another problem with BIOGEME with respect to a logit. It's that you have just one data file. You cannot read multiple data files. And this is a limitation, because if you work with stated preference, many of my models are based on many files. For example, if you work with NHTS, what I like to do is to keep households separated from individual, from vehicles, and from trips. I like to, because it's cleaner. You can see if there is a problem, and in many times you have problems. You can see where the problem comes from. That's why my student, that she's working with car ownership, and she deals with 4 different files. That's why she's first using a logit, and then she translates into another software. But anyway, this is BIOGEME. You need to have one data file. You need to have everything in one data file. The other things about BIOGEME, he wants you to give, so the data file must contain, the first line must contain the name of the variables. So you need, really this is text, like, you know, the identification, the alternative specific constant of the car, train travel time, train travel cost. So you need to give the names, because he's going to read that line and assumes that these are the X that you can use in your model. And then you have all the observation. That is different from other structure, especially if you work with code from Gauss. This is totally different from code that you will see in Gauss, because Gauss is a matrix language. So for example, all the code written by Ken Train, all code written by Ken Train and Chandrabat and ourselves, Hamlet, they are kind of matrices language. What does it mean? It means that instead of having this, which are long line, you have something different. You have, on the column, you have the alternative. for example, here we have 3 alternatives, right? And then on the line, you have the different variables. So here you have, for example, x1, that can be train travel time, x2, which is train travel cost, x3, 4, 5, and 6, which is Swiss Metro travel time, Swiss Metro cost, car time, and car cost. And you have a value here, right? So you have one block. And this is one person, or one observation from one person. Now, the way CAN-TRAIN works, he also wants you to give the availability. The availability is a line, and it means that you add here the availability. You know what is availability? Remember that we defined the total number of alternative specific constant, but each individual can have a different set of alternatives. So for example, suppose that I don't have a license, suppose that this is car. I don't have a license, so it means that the car for me is not available. So 1 is available and 2 is available, but car is not available. And also you can give the choice in CAN-TRAIN software into 2 ways. Even you give the choice here, or you give the choice in another file. So if you give the choice here, and suppose that here I've chosen train, so I have 1, 0, 0. So this is the vector of the choice. So it means that one observation is 8 lines. It's a block of 8 lines. So if you have 1,000 respondents, you have 8,000 lines. You expect to have 8,000 lines. And this is because it's matrices. You see, this is good for because everything at the end of the day, as my students in statistics says, at the end of the day, we are always multiplying matrices. If you know how to multiply matrices, you can implement any model of any kind of this model. While if you don't do this, suppose CAN-TRAIN wants a vector, he wants the choices. So for example, 1, this is, he wants just, if I choose then a car is 3, Swiss Metro, and so on. So if you specify the choice in a separate file, you need to tell him. Yes, 2 ways. Now in CAN-TRAIN, there is another peculiarity, and also our software, is that if you work with panel data, you need to tell him how many observations from each person. So for example, if you have 10 people, you need to tell him that, for example, you have 9 observations from the first, 8 from the second, 6 from the third, 9, you know, how many observations, because then he can calculate the correlation among the observations from the same person. And he calls this train 99, train 96. Anyway, you can read instruction about this. It's quite clear. This BIOGEME is organized this way. It's just a normal database. It's nothing. It's not matrices. Now, these are the sections that you need to fill in order to have the model specified. So you have the model description, kind of blah blah, but this is also important. When we calibrate model, kind of give instruction of what this model was, because if you take this model a year later, you have completely forgotten what you were doing and why you were specifying the model that way. Then you specify the choice, the betas, the utility. You make all the calculation, expression mix, all the algebra, you know, scaling, adding, multiplying, and so on. Exclude, it's for data cleaning, or it's for estimating the model on particular segments of the population, and then you have the model. Okay, as I was saying, model description is just kind of comments. What is this model? When I estimated, I'm happy with this or not. Model description is, it means that I have a logit with 3 alternatives. So I'm going Again, this is kind of comments. It's not doing anything, but it reminds me that I'm working with train, car, and Swiss Metro, which is an hypothetical high-speed train. It's not really, so this is SP. Then the choice, you need just to give him the variable that is the dependent variable. For example, I don't know how it's called. It's called, for example, in the file, it's called choice. And these are comments, the parameter. So now he wants you to list all the parameters in your model, and that's the way he wanted this. So he wanted the name of the parameter, right? Remember, these were the way they were specified in the utility function. He wants the default value. So if you start from, you can sometimes, to facilitate the estimation, you give a starting value. In logic, it's not necessary, but sometimes in nested logic, it helps. In mixed logic, it doesn't really help. But for example, in our discrete continuous, when we calibrated the probit, we kind of trick the system in the sense that it takes a long time. So if we have a good starting value, we give the starting value, and then we do just the last iteration because probit can take, I don't know, sometimes a day to be estimated. So it's useful to have a starting value, a default value. Now, this is another thing that BIOGEME does. He wants you to fix a lower bound and an upper bound of the parameter. And I think this is also for numerical reason, to facilitate the optimization. So you are telling the software not to search for beta that is 100. It won't make any sense. So it kind of gives a lower bound and upper bound. And then this is very important. This is this status variable. So status not in the same sense of dynamic discrete choice model, but it's 0 if you want the variable to be estimated, and 1 if it is fixed. So remember that we said we needed to fix one alternative specific constant because otherwise we won't be able to estimate the model. So he's fixing the alternative specific constant of the Swiss Metro to 0. And this is also very counterintuitive. It's fixing to 0 and the status is 1. When status is 1, it means do not estimate it. Or for example, what you can do if you have, sometimes you want to fix some variable, right? So for example, say travel time is 0.01. So you say travel time is 0.01 and the status is 1. So it means that it will be fixed and not calibrated. It is also good, this is also good when you apply the model, because then you don't want to estimate the coefficient. You want just to use the coefficient to produce the market share. Alice says that the specification of one alternative must start at a new row, otherwise it gives you error. And you need to specify 4 entries. So the identifier of the alternative with the numbering convention consisting with the choice. All right. Okay, so she's saying that this is the way you specify utility. So this is very important. You know, here the utilities are this, right? Are the column, right? Because alternative 1, this is the utility. Here, so you needed to give him an identification, and this number is the same number that is in the choice. If in the choice train is identified with 1, you needed to give him 1 here. So the identification, the name of the alternative, the availability. So the train it's a variable in your model if train is available for that person or not, or it's a variable that you have constructed. For example, you say car is available if license is 1, if I have a license. If I don't have a license, car is not available. And then you have a linear parameter expression, right? You have the alternative specific constant plus the time plus the cost. So this is the coefficient beta time, right? Beta time, beta cost multiplied. This is the name of the variable in the file, and so on, right? So you have 3 alternatives, 1, 2, 3, and the utility. So identification, name, availability, and utility. Expression is all the algebra you need in the model. My suggestion is try to do all the calculation here. So try to, so if you have collected the data and you have a data file, try to not make too many modifications when you work with the data. So do all the transformation in here because you keep track of it. You can do all kinds of algebra, basic algebra. For example, here is saying that SP is available if this variable it's not equal to 0. So this is, or I don't know now, but this was originally coded in C++. So you can recognize this. These are operator in C++. So. And also, you see the scale is dividing car time and car cost by 100 for computational issue. So that's what he's doing. Exclude. This is very important. In each model you estimate, this exclude is important for two reasons. Because exclude will give you the possibility to clean the data. For example, if you realize that some people, they did not declare their choice, you exclude them. Say exclude if choice is 0. Or you can say exclude if travel time and travel cost, for example, are values that are really, they don't make sense. For example, if they say travel time was 24 hours and you are working in an urban area, this is for sure wrong. Or for example, for some people, we were saying yesterday how difficult it is to have travel time and travel cost estimated. So for some pair OD, sometimes you don't have information. So you exclude if travel time and travel. But this is also important when you want to do segmentation. You want to estimate different models for different purposes. For example, here is saying, what is it? So yes, different purposes, right? So yes, probably yes, commute, yes, shopping, yes, leisure, and other. So here the syntax is saying that exclude those who have choice equal to 0, and exclude if purpose is not equal to 1 and not equal to 3, right? That's what he's saying. So this is not equal, and this is or end. End. Okay. Anyway, this gives you the possibility to estimate different kind of model. You specify the model, and so this is MNL, but can be NL, can be ML, which is mixed logic, can be GV, can be latent classes, and so on. So yes, different way to estimate that model. These are the expressions. Let's just see. This is website from Michel. This is BIOGEME from EPFL. This is what he has. So yes, different version, but let's see what he claims he can do. He can do logic, binary problem. So I was right. Just binary problem. Nested logic, cross-nested logic, multivariate extreme value models, discrete and continuous mixture of multivariate extreme value models. It means means mixed logic with discrete and continuous mixture. So. Models with nonlinear utility function, which I think is the log operator we were discussing last week. Models for panel data and the heteroscedastic model. Okay, so that's what we can do. So this is BIOGEME EPFL.ch. Okay. Now, yes, different version. I don't know the. So you can download the source code. This is open source. You can look at this source, at this code. Although we have tried to open the code and never understood, it's very difficult. When a code is written by somebody else, it's very difficult to get into that code. So he has an executable command for Windows and example. So what I did yesterday, I downloaded BIOGEME. The version for Windows, it works, it's very easy. This is the computer interface. So not much, but so you needed to specify the name of the file. So you select the file. Let's take one from these examples. For example, logic. And then the data file is this is from this example in this data file. So you have the Swiss metro, and then you say estimate. is reading the data, is estimating the models, and probably he has results which is displayed to file. So this is what you finally see results out of one of these model estimated. So this is usually what you get. So he's saying you have this example with 3 alternatives, train, car, and Swiss metro. You estimate 4 parameters. You have 6,768 observations. This is the log likelihood at 0, right? No parameters estimated. This is the final value of the log likelihood. And this is the likelihood ratio test with respect to 0. He has a rho squared and adjusted rho squared. The difference between rho squared and adjusted rho squared is that the adjusted rho squared takes into account the number of degree of freedom in the model. Final gradient norm, he has converged with 26 iteration, and he is lucky enough to have, well, this is easy, if I calculate analytical action, so he calculated the statistics. So you see the estimates, right? This is fixed because it's 0. Then he has 2 alternative specific constants and the travel time and travel cost. Everything is very significant. Not much to say. These are negative. You see, these are negative, significant. These are also negative and significant. Value. This is 1/1 multiplied by 16. So yes, a value of time of over 60 Swiss franc per hour. But anyway, that's good. And remember that usually these numbers are what I expect from this model is 0.001 for time and 0.1 for cost. Remember that he has divided this by 100. That's why you get so high value here, right? Because if you have divided the variable by 100, you get the higher coefficient. So this is the kind of check you do, right? You check if everything is significant, you check if they have the right size, and you check the value of time. So this is when you get results, this is the basic things that you need to do. And it gives also some utility function. Well, this is the utility function. This is the variance covariance. And you have the correlation. So you check the correlation between time and cost, because remember I said sometimes these are highly collinear or fine. You start to are in trouble when you have 0.6, 0.7, 0.8. Then you really want to see why this. And this correlation with alternative specific constant, they don't really matter. So even if you have 0.6 here, doesn't matter. Sometimes it's highly correlated, but they don't affect your model. Okay, so this is a simple multinomial logic. Let's have a look at the model. This is the syntax that you needed to write. Choice the betas with one constraint to 1. This is another syntax. These are the utilities, the expression for the utilities, the scaling, the exclude, and the model. Okay, so this is logic. Now here's a number of examples. Nothing changes up to nothing changes, so everything stays the same. So you can reuse what you have written, except here. Now you see the model type is an L instead of an L, and you need to tell him which is the structure, right? So what he has here, let's see what is the structure. So the structure here is you have train, and you have car, and you have Swiss method. He's saying that he has a tree like this, in which these are the existing alternative, and this is the future alternative. Right? So he's saying that alternative 1 and 3 are in the same nest, and 2 is outside the nest. So this is a kind of strange, odd, my reviewer will say odd nest, because he has existing alternative 1 in one nest and a non-existing alternative outside. So he decided this. So you also see that he fits this to 1. So there is in reality no nest, and there is a nest here with a coefficient to be estimated. So he is estimating the theta of this, while this theta is fixed to 1. Right? So that's what he says. Be careful, because let's run this. So I'm running the nesting. Okay? So everything is the same, except that you are estimating one more coefficient, right? You are estimating the theta of the existing alternatives. And you see that, surprise, he has 2 as a coefficient, and it's highly significant, and the other one is fixed. Now, this is due to the way this nested structure was normalized. Now, this normalization is from the top to the bottom, and it gives you a theta that is larger than 1. The way I've taught you nested logic is normalized from the bottom to the top. Remember that I said for many years we have estimated nested logic that were not normalized. Now, taking into account the way you normalize this utility, this is completely equivalent to a nested logic which is normalized from the bottom, which I prefer because it gives you a theta which is between 0 and 1. It does this, and this is called nested from the bottom. It's exactly the same model as before, except that the normalization is done from the bottom. So let's see what it's getting. Yes, it's 1 over 2, which is about 0.5, right? It's just the inverse. The only problem, I think, because I've seen this during the lab with my students, when he does this, he doesn't allow you to estimate more nests. It just allows you to estimate 1 nest. If you want to estimate multiple nests, you need to use the other normalization. You know, it's a way he has programmed this. Also, Michel is very busy, he doesn't have the time, so he's not doing just this. He's doing this, 15 students, 15 projects, so he's very busy. So, this is more consistent to what you see in the book, right? Theta between 0 and 1. It's more intuitive, but it's exactly the same thing. If you compare this, they don't change. The coefficient don't change, the final value of the local likelihood doesn't change, anything changes except with this normalization issue. Right? So let's have a look a little bit at the example that he has. Right, so this is the description of what he has. So he has an example of logic. You see that he has this Python BIOGEME, but I'm not very familiar with that. So let's look at this. So he has a logic, logic with weight, scale. Scale means privilege and static preference. I will show you. Transforming the variable, I don't know what it means for that. This is normal mixture of logic, so this is mixed logic with coefficient specified as normal. Logic with numerical integration, so it means that, oh yes, not improvement. This is with simulation. You wanted to do this with numerical integration, never done it. Uniform mixture of logic, it means mixed logic with uniform distribution for random coefficients. Not implemented. Discrete mixture of logic, so it means that he estimates quantile. So it means that he estimates the 10% quantile, the 20% instead of having a continuous. This is the discrete mixture of logic. Yes, box-Cox transformation, many people have used this box. They are not popular anymore, but 20 years ago people were doing a lot of stuff with this box-Cox transformation. Yes, nested logic that we have just seen, nested logic from the bottom. Yes, cross-nested logic, yes, error component with panel data. So this is mixed logic with error component and panel data. Yes, error component with panel data normalized. I don't know what it means. This is mixed logic model with correction for choice-based sampling. So this is something that he has done in research with one of his students, because Michel does mainly route choice model, and he has a problem of choice set formation. I don't really do that, but the problem here is what my colleague Dr. G.L. Chang always mentioned, that when you do route choice, there is a lot of correlation between the different paths that you generate, and there are millions of these, and he has a particular model. This is Finger-Yerler, it's a paper up here, classification such quantity. So this is for this model. Yes, panel with latent classes. Yes, semi-non-parametric. Yes, remember my B-spline? He does something that is similar, but he uses polynomials. So instead of, I use B-spline, he uses polynomials. But it's a flexible way of doing mixed logic. Then he has log normal, mixed logic. You see that he does different log normal. So he has this, and he has with the derivatives, because log normal is very difficult to estimate. So probably people were saying, you know, I cannot estimate this. Can you give me something that is better? And he was trying with derivatives to speed up also the process, because this maybe need it's difficult. Latent variable. With discrete responses and latent variable with continuous responses, you see that why many people are using latent classes and latent variables, because these are readily available here in BIOGEME. Then he does this outside. Oh, it is not. Oh, no, this is not here. Oh, it's here. It's in Python, so it's in the Python version. You needed to open the Python version in order to do this, but it's feasible. People are using this. I've seen many people using this. Another thing that I don't like in BIOGEME is that statistics are outside the model. You know, it's very important to have statistics readily available when you estimate the model, because you want to see travel time, how many people have zero travel time. You want to see, you want to clean the data, and if you have this outside, it's kind of difficult. This is application. Remember that you have seen many applications, and you can use the coefficient estimator in order to test the validity of the model in application, or to calculate elasticity, or to calculate scenarios, to apply the model for different scenarios. All right. So you see how many things you can do with almost all we have seen. You can do with BIOGEME. This is also my first time I open this with you. I want to see how it does mixed logic with normal and with error component and pan. Let's see if we can understand how that. Yesterday I was trying to do this, but it got stuck here. I don't know why. Either it takes too much time, and yesterday was very late, but I don't know what it's doing. It works because it works on the logic and nested logic, but I don't know. But people, you know, have been using this for estimation. But so let's give him some time. So, given that the normal is empty, I don't know why. Let's see how it does a mixed logic, right? So this is mixed logic with uniform distribution for the random variable. So it's mixed logic, random variable with uniform distribution. Blah, blah. Oh, you see that yes is sigma on the, remember that you need to estimate a beta, a mean and a standard deviation of the variable. So this is for the uniform. So this is a uniform. So somewhere it should tell you that is, so for beta time, you have to estimate a beta, and you have also to estimate a sigma. So that's where you are telling him, estimate time is uniform B sigma. Right? That's why what he's telling to BIOGEME. So beta and sigma. And what else? Again, he has MNL. He doesn't. So he says kind of this is a multinomial logic with random parameters. So he's not changing this. I noticed also this yesterday, and I think that's it. That's the only change. Oh no. Oh no, this is LaTeX. So the only change is here. You have beta time and beta time sigma, and you are estimating it. And so that's very easy. The rest doesn't change. The rest is exactly the same. You should have somewhere simulation. Oh, draws. You also need to. Oh, that's why it doesn't work. Because here's 100,000 simulation. So this is a very high number. So by the time it's generating all this number, it will die on my computer. So this is the problem. So the difference between estimating a multinomial logic and a mixed logic in BIOGEME is mainly that you need to specify the sigma, right? And you need to tell it how many draws you want. Now I don't know how it's generating these draws. If these draws are just Monte Carlo, or if these draws are quasi Monte Carlo alpha. You need to put it in the instruction in order. Now you know what it means. So I don't know if these are just random draws, or if they are quasi random draws from alpha. I don't know. So this is the only difference, but BIOGEME refuses. Let's see if I change this. If let's see 100. If he likes it. Yeah, you needed to play around, but you needed to understand. If it doesn't work, this is the main job, right? You needed to understand why it's not working. Let's see if now it works. You see? Now it's working. It was just that it was generating 100,000 rows, and my computer was just okay. So it's estimating. You see that it's not as fast as logic or massive logic. So, and this is one random coefficient and one constant coefficient. So. And you spend your days looking at these runs, and that's I spend my life. This is just 100 rows, which is nothing. You need at least 1,000. All right. Oh, it is computing the action. You see that this is also troublesome. But we can get results. So mean, sigma, and both very significant. And probably we are increasing a lot the rho square. I don't remember what it was before, but given that this is highly significant, I think we are doing well. All right? So what I would like like you to do is exactly this. I hope that out of this class you understand what is behind the mixed logic. So if it's not working, which happens very often, you see, I was able to retrieve the problem. I said, oh, this is the problem. It's because it's generating all these numbers. So you should be able to understand this kind of mechanism. Let's also see. Oh, the other thing is that you need to close this every time you want to restart. Let's see error component. So this is panel. Okay, this is kind of a fully heteroscedastic model with panel. So remember what it was a fully heteroscedastic model with panel. So it means that he has a sigma on all the alternative specific constants. So it means that he allows different variances for the error of each alternative. Remember I said what is the difference between homoscedastic and heteroscedastic model? And we say all the GV, they are homoscedastic. It means that you have the same variance for all the alternatives. So it means that the variance covariance matrix of a multinomial logic is something like this. Right? Where theta is pi squared divided by 6 over lambda. Right? And lambda is normalized to 1. So this is homoscedastic. So logic, nested logic, all kind of GD, they are homoscedastic. Heteroscedastic model is when you have a sigma 1, sigma 2, and sigma 3. Right? Theta 1, theta 2. So you can do that in mixed logic if you give a sigma to each alternative specific constant. And this is exactly what is true. Sigma car, sigma Swiss metro, and sigma train, and it gives it gives one of these, like you see that yes, this sigma here in each alternative multiplied by 1. It's like, yeah, it's like a kind of error component in each. It's not like it's not really an error component, but it's specified like an error component, because error component will be just in some of this. For example, here, if you want to have the nested, this is an heteroscedastic panel. And let's see how he accounts for panel. He accounts for panel by doing this. So I believe, you know that this is SP. So SP means that he has multiple observations from the same individual. You have seen that yesterday, right? So it means that all the observations from the same individual have the same ID. So if individual 501 gave 4 responses, you have 4 times this. Right? So this is the ID, and this is the number of responses. So 1, 2, 3, and 4. But the ID is always the same. So he can count how many observations belong to the same individual, and then account for correlation across the same individual. Right? Can you see that? And this is the way he does. And he also needs to specify which belong to this panel, what belongs to this panel specification, which are all these sigma. Right? And I think that's it. The rest is the same. So let's change this 100,000 here to 100, and let's try to run this. Oh, let's say 1,000, which is more realistic. Let's see how much time it takes. So any idea? Just throw out idea. Why it was kind of faster in generating that? But you see that he has not done anything yet, not even one run of estimation. So it takes time. He was a little bit faster because he needed to generate less random draws because it generates one random draw for each individual. So if multiple observations are associated to the same individual, you need to generate less random draws. That's why. Because if in normal mixed logic, without a panel, you need to generate a random draws for this, for this, for this, and for this. While in panel, you generate one random draws just for the individual. Remember that I said beta is constant across individual. That's what he's doing. That's why it was faster. Faster, relatively faster, because we are still stuck there. Now you can touch how difficult it is. I'm glad that we had the time to do this. Okay, while he's thinking, let's see what else is there. Okay, so this is, he says that this is a G, it's a cross-nested logic. So we have seen that. We have seen that cross-nested is when an alternative can belong to different nests, right? Generalization of logic. So let's see how he does this. It should have a nest somewhere. So it appears that he has two nests. He has existing and public. So he has existing and public. And he has train in the middle. So existing is current train, public is train and Swiss method. So this is a cross-nested logic because train belongs both existing and public. So that's what he's doing here. He has existing and public and both to be estimated, right? Then he says that this is kind of how much train belongs to the existing, how much to the public, and this car belongs just to he fixes it. So he says that he says that this shaded alternative is just train. It does not concern a car or Swiss measure, right? That's what he's saying. And he's constraining that because at the end of the day, the alpha of train plus the alpha of train, so this percentage of train in existing plus the percentage of train in public, this must be 1, right? Because the percentages of how much it belongs to one alternative and another must be 1. So this is what he does. So this is it. Let's see the results of this, what he gets. This is the estimation. This should be fast. Okay, this is the idea. So it's this he has a problem. So this is he has a problem with CNN. Let's see the other one. No, runtime error. He did not. I don't know why. If he has this example, they should work, but I think we have seen almost everything. So I leave it to you the rest. So we have seen logic. I want just to show you the scale. This works. I know that this works. Scale means stated and revealed reference data. So how this is organized. So if you look at the data, he has 3 sections. He has an RP section. And he has an SP. He has RP data first, and then he has SP data after the RP. And this should be organized in a clever way because you kind of have 4 quadrant here. So you have RP data here, and you have SP data here, and all 0 and 0 here. Why this for the availability? Because these alternatives are available where RP is not 0 and vice versa. So usually I organize the data this way, that I have columns that are for RP and I have columns that are for SP. In order to have the availability is much easier to specify. So he says that this is identified with group variable 2, and this is identified with group variable 3. So it means that when this group variable is 2, you are dealing with RP data, and when this group variable is 3, you are dealing with SP data. So you need to tell him this. And this is what he's doing. So you say, there are groups. So RP is one group, and SP is another group. So if the group number is 2, then this is RP. And if the group number is 3, this is the SP. And you see that by fixing the theta parameter of RP to 1, he's saying just estimating the theta for SP. Remember what I said yesterday? We cannot estimate the theta, both the theta RP and SP. So the scale, we fix one and we estimate the theta SP with respect to the theta RP. That's what he's doing. So he's fixing one and estimating the other one. So this is the only difference. So you see that once you understand the model, it's relatively easy to adapt that syntax. But you need to understand what's going on, and you need to understand, especially when something goes wrong. So you can do quite a lot of stuff with this. And that's all I have to show. I'm open to a question, or if you want to see more, but this gives you an idea about what it is. Yeah, I really enjoyed this day here. Thank you very much.